after the fact. All right, we're good to go.
Okay, maybe I should start.
Sounds good.
So ideally, everybody should have Conda installed and they should be able to open up Jupyter Notebook. If no one has, if there are people who hasn't done that step, maybe we could take 5 minutes to see if it is possible to get you there, or we could share some other materials where you can do whatever we are doing at a later point in time.
Do you want to give a quick introduction of the series, what you're hoping to accomplish, and then people can work on the setup while you do that, and then we can come back to them and just see where people are at, if they have it already or not.
Okay. Yep, so I'm Suryatapa Roy. I go by Roy usually. I'm working as a data scientist at Chada, which is a startup in Calgary. I did my master's research at the University of Calgary under Dr. Yogin. My research discipline was
one person on the call. Hey, Larry. That's muted. You're good, Suryatapa.
Okay. Yeah, so my research topic was an integration of machine learning and human intelligence and human-computer interaction. Right now, I work on natural language processing and deep learning, essentially. I started this AI fundamental series because, first, we are all in this thing that we're going through, and we want to all learn things and make the best use of our time. And in the past, we have set up meetups like Deep Learning Fellowship and other AI-related events. And I received a lot of feedback that though those things are great, a lot of people don't have the basics or the fundamentals set up to follow along some of the more advanced things or some of the more cloud-based things. So a fundamental understanding of the different algorithms and what machine learning generally tries to achieve, that is very important for everybody to start making use of these tools on the cloud or of these other sessions that GTTYYC hosts. So and implement these more constructively and more towards the algorithms and how you build models and deploy them. So considering this is like the first week and like the first session, I'm gonna give a very rudimentary introduction to what we are doing. And if people are slightly more advanced and know this stuff already, just go along. And if you have any thoughts to share or corrections, please feel free to add your comments.
Perfect.
Okay, so firstly, we need the setup. This slide has linked to the documentation for Anaconda setup. I had also sent an email with links to how to set up Anaconda and the basic stack that we're going to be using through the series. And then the first one is a link to this slide, which has other links to follow-up materials. And the other one is the GitHub repo that we're going to maintain through this course. So everybody should clone this GitHub repo and start up Jupyter Notebook from that. So how that would go is, this is how I do it. You might be on Mac, and you might have your own way. So this GitHub repo is where I have these two scripts. I'm gonna start Jupyter Notebook here, and that opens up a tab in my browser like so.
If you can make that a little bit bigger, I don't know if that's possible, and then it'll make it a little bit easier for people to see.
You mean this tab?
Yeah, just that tab. I don't know if there's a way to make it. Yeah, there you go. Helpful. Perfect.
So once this tab is opened, you go open up the script. This is what opens up. This is the folder, and then you have two scripts. You're gonna start off with the first script, which is the PyTorch basics. Now, before we start running some of the code, it's needed to talk about the fundamentals a bit. For those of you who are very, very new to machine learning, I don't usually like to call this like a beginner's introduction, because I don't think there are any beginners in machine learning. Machine learning is a way of making computers understand things the way humans do. So machine learning should come very naturally to humans. They should already, if you can break down your thought process before you make decisions, or before you predict things, or you make logical derivations in your life, if you can break down that process, then you can understand machine learning very easily. There are like tons and tons of examples out there of doing this comparison. One would be like, how did we ever learn the color of fruits? It was taught to us that oranges are orange, and apples have this texture, and it's shiny, and it has a red color most of the times, and different objects have different colors, different shapes. When we are learning as children, we learn to differentiate things based on shapes, and then recognize things based on their colors and these different attributes. But in the beginning of time, we were taught this. We were given the data and told that all these fruits are round, and then some of them are orange, some of them are red, some of them are green, and then you call them different things. So these are labels that somebody told us that these were these things, these were these things. So generalize in your mind what each object is. We were given that data when we were kids. But in the beginning of time, people didn't know what these objects were. They needed to call these things something. First of all, they didn't know what round was. So they looked at a lot of objects and saw, okay, all of these things have this certain shape, which is like a circle. So they called that shape round. So that would be something like a clustering, a grouping of things. Before, there were no labels. There were these round objects, there were these square objects, there were things that didn't have shape, like water that flew, like birds, and there were trees that were abstract shapes. But people over time knew how to group things, where they grew, what colors they were, what they did. And these groups, then they named something, they called it a label. And that's how the process began. And because there were certain set standards in the beginning of time, that these things were going to be called this and those things are going to be called that in different languages, people later on started teaching the children what these things were, so that everybody could communicate on that same language, or on the same information exchange platform. So machine learning is just the same thing. If you have data in the beginning of time and there's a set process, people know what this is, what the label is, what you want to get out of that system that you're building in a computer, and you have this data preset, you're just trying to teach a machine to generalize these learnings and then come up with something, then that's called a supervised machine learning paradigm. But if in the beginning of time, like there were no labels, still today there are many problems that doesn't come with labels, like things in nature that we still don't understand, things in space that we don't understand. In general, when you look at a collection of people or something, you do not come up with labels at the start of the process. So those things become unsupervised learning, where you're first trying to teach a machine how to group things, and then do something from there on. So those are basically the two different things that happen. Did someone have something to add at this point?
Who here, I guess maybe a good question is, who is familiar with these principles so far? Just, you can speak up or you can post into the chat there.
I've just got a basic reading knowledge. How's that, Greg?
And yeah, that's fair, John.
And it's been a while since I've been, but
yeah. I would say I
think learning by example. The code is a wonderful way to clarify all, make it concrete.
Okay, great. Yeah, no, that makes sense. Anyone else have experience in this area or a lack of experience in this area?
And I've just installed my Anaconda here. Perfect. But I don't know if I can get to Jupyter, but I'm great that you're recording it, and we can follow up later here. But this is wonderful.
Perfect. Yeah, I would say lack.
So I just wanted to add, it's been a good 10 years since I programmed anything at all. I moved into management and I've been quite busy with that, but now I want to get back to basics. So I started with a Stanford course, and I'm doing this, and I'm really hoping to get my hands on coding and learning about machine learning.
Awesome. Were you able to get your machine set up?
I'm in the process of setting it up. I actually missed the email from Sudhir earlier.
Okay.
Likewise, yeah.
But I'm setting it up.
Perfect.
Okay. So if people have that set up and they have Torch set up, then in the PyTorch basics, that first section. So how Jupyter Notebook works is you have these little sections in the notebook where you can run code individually, as opposed to a full program where something compiles first and then runs the whole program at the same time. This one you can write code as you go along, and that's why Jupyter Notebooks are so great for these kinds of interactive sessions. So if you just clicked on this first tab and did a shift enter, or you can also do a run here on top, then it will run this line of code and it will import these libraries. So now PyTorch is Torch and Torch Vision, and it has different sub-modules that we're going to be using. So it will import that, and that's basically like if you have that set up and installed, that just boots up that base layer code in your memory space right now. And if you don't have it installed, it will probably throw you errors. But you're just kind of linking your code, what you're writing now, to this base library. And so kind of before we go into these data structures and the math, some more details of the kind of problems, then you can break up supervised and unsupervised learning into. There are mainly two kinds of algorithms. One is like a continuous space, which are called regression problems, where you're trying to come up with a value, like a floating point value of how much of something, right? If you're asking yourself questions like how much, to what degree, like what is the composition of something, then those problems are likely regression problems. And then the other half is prediction problems or probabilistic problems, where you're trying to figure out if something is true or false, which of these finite things are possible, which object is out of these 10 things this most related to. So those are predictions or likelihood problems. So those are two kinds of different ways of looking at things. The most basic way of explaining this would be, say if you were making dough, right? And given how much bread you wanted to make, or how much whatever cake or whatever you wanted to make, you needed a certain amount of flour. And now given you are either making a cake or making a bread or making some other pasta or something like that, each of them uses flour and water, but how much flour and water and what other ingredients are used, they differ. So now you can say there are 3 different restaurants or bakeries that make bread very differently, and you wanted to replicate the recipe of some one person. But then there is a general formula of making bread, of how much water and flour you add and what other ingredients you add in it. But then this other person probably does something very special to it, or adds some other degree of water to make a different kind of consistency. So you would, for you to replicate this process, that's kind of like a regression task. You first need to collect the data, like different people across like hundreds and thousands of restaurants make bread like this. So this is how much of this goes into that. And so when you are trying to add things to build something, you're building this proportion of things from this general principle that you have come up with. But then that is kind of like building a general machine learning model, and then you kind of fine tune a general model to a task specific thing, where you look at this particular kind of bread uses a slightly different formula. You kind of take that general principle and then use data from that particular bread only, and kind of fine tune that model, that those general principles and rules to that specific task. And that is kind of the kind of models that you see out there in the world. You have like image processing tasks, which looks at thousands and thousands and billions of images, and kind of comes up with a general principle of what pixels are and how they're related, how things go together. But then if you're trying to classify between dogs and cats, and that is the only problem that you care about right now, you then fine tune that general principle of data of images, and you fine tune that only on cats and dogs to separate the patterns between those two. But then this is kind of like how much of something you want to add to build something, or given that something of this proportion was there in a bowl, you can predict what bread or what pasta or what cake that this would make. So that is kind of 2 ways of looking at it, like whether it is a classification or it's a regression problem, whether you're trying to come up with like how much of something was added, or whether this is a bread or this is a pasta, or which kind of bread that is. So these are the kind of different ways of breaking down these 2 areas of probabilistic thinking and continuous space thinking. Did that make sense?
So maybe the easiest way to explain it is, or if correct me if I'm wrong, is in normal systems we have the data and the rules, and then that creates the outcome. Whereas in a machine learning system, we know what the outcomes are, we know what bread is, we know what goes into bread, and we use the data to create the rule set.
Yes.
Okay.
And we kind of do this process when as people as well. So
Yeah.
if we like didn't know the recipe of something, maybe a book gives you a recipe of bread in a certain way, and that has come from looking at thousands and thousands of recipes of bread over thousands of years of how this general process of doing something works. But then there might be a specific kind of thing that one person has written, like a special kind of bread, like banana bread, and it's slightly different. And then the same way we learn things or we process the different information and build things, the machine learning does the same. It's just we try to break down this logical process. We don't often think about these things, right? Like what is that we are doing, what is that we are thinking. But to train machine learning models, to build them, we need to kind of break down the process so that the computer can do the same thing that we do when we think.
Yeah, that makes sense.
So this series, there are many kinds of. Sorry, was somebody saying something?
Well, I suppose if I could just jump in. So it's a trial and error experimental process, iterative process to what do you know and what would you like to know, and that's essentially what machine learning is. It's a formal process, I guess.
Yeah.
Okay.
Yeah.
You kind of start with John. You start with the outcomes in some cases where you know what you're trying to get to. You're trying to get to bread that's made, and some of the data might be the ingredients, but you don't know how to put those things together. You may not know how to put those things together to make it so that the bread comes out at a nice, perfectly brown, all those things. So has a certain density or otherwise. So
you have a trial recipe and see how close you get, and then you say, okay, well, if we change this and so on, you iterate. Yeah. Okay.
Yeah.
Makes sense.
I have something to add to John. Can you guys hear me?
Yeah, absolutely. Go ahead, Jay.
So I think John made a point, trial and error, and in the technical term, we actually call that, oh, you are learning from this data, and when you are training the machine learning model, and you want to learn good way from your data, whatever you have. So that trial and error then boils down to loss, that you'd have data, you have 10 example, you are learning from 10 example, but you haven't seen much data. So like now you want to predict something, the next thing you cannot be sure that, oh, this thing will be apple or this thing will be orange. So trial and error gives you good enhancement, and then we have this loss function called in machine learning, specifically in technical jargon, that will help to build good machine learning models.
Yeah. So the loss is essentially how close you were the first time you tried this process, how close you got to that difference of what was true and what you thought was true. That is the loss, and then every iteration you try to minimize that loss till you are satisfied with the accuracy of how good your model is. So I think, yeah, the basics are there. And now machine learning has many different kinds of algorithm sets. Supervised, unsupervised are two broad principles. Deep learning is generally a supervised context. We are going to be mostly focusing on deep learning in this series. There are like many different algorithms that deep learning has evolved from, and if someone's very new to machine learning completely, it'd be also worthwhile to learn those fundamental algorithms. Right now, deep learning is like the buzzword, but there are many problems, and so deep learning needs a lot of data, and in the time we live in, we have a lot of data available, and once you have a lot of data, deep learning models are very good at generalizing principles of rules and patterns, and that is why there is so much interest in deep learning right now. But before, when we didn't have that much data and we still wanted to make these models of these systems and processes, we used fundamental algorithms, and depending on your problem, deep learning may or may not be suitable. But if you have certain problems and you want to talk about them, we can talk about it at our forum and other pages and stuff. So this is essentially a typical example of a neural network, and deep learning is essentially variants of neural networks. This is like a very fundamental basic level, and if anyone has signal processing like background from electrical engineering or something, this is a very simple evolution of models that we had in signal processing, where you had inputs and that went through these transformations to come up with output. This is all just information in digital format that's flowing through and is going through different transformations till it comes out as the desired output of that system. Here in the input layer, you have these features of the data, which is like age, income, employment. So then maybe you are trying to predict if an individual is married or single. So there you could have a lot of data about this person, where they're employed, what their address is, what is their pattern of walking, what food they would like to eat. The kind of data that people collect or is able to collect from these different apps and softwares, and in general browsing history and things like that. There's a lot of data you can collect about an individual, but which are these, of all of that information, which are these 3 or 4 very important characteristics that leads to a prediction? That is most of data science and most of like real world application, right? Like you can build model, and there are researchers and scientists over years that have come up with different models that are very good at achieving a certain task. But what is that input that predicts that output most accurately? That is the whole problem formulation task. Right now, we are gonna today just look at how to build this network, how to get this input feature data in there, how to connect these layers, how many layers that is needed. Like each of these layers are transformations of this input data, and each transformation probably abstracts something from this. So if age and income had this correlation, that had this very deterministic correlation to being married or single, this network would learn this correlation and predict, have like a weight that helps in that prediction. So think of married and single being y, which is like 0 or 1, the prediction outcome of this network, and you have 3 features, x1, x2, x3. And so now you're forming a function which is like a function of x equals to y. Now this function can be weighted. So if it was like a linear function, then y was just some constant times x. It was just a line that had a certain angle to the xy plane. Or if you were coming up with hyperbolic function or something more complex like a sinusoidal function that went up and down periodically, there is a set function that you're trying to learn from that data. But in these kinds of human processes, we don't know what that function is to begin with. We can only approximate that function using that data, and this network is what is approximating that function. It is saying that I'm going to have h1, h2, or how many ever hn hidden units per hidden layer, and that one is going to go some transformation from this input. So it's going to first build x, some function to build this h, and then h will be some sort of an abstraction of this information. Maybe some correlation is there, maybe some like zero correlation or no relation is there. So some of these weights will just turn off and say there is no pattern here to be learned. Something will learn negative, that something when it goes up, goes down. These things between the input, the first layer will learn. Then there might be another set of rules there where this correlation between these two things again have some other relationship to the other parameter. When something was negative, the correlation between these two things went up. When something was positive, the correlation became zero. There may be some other rules between these operations. And then finally, these rules that the network learns helps in predicting that final outcome. And how these rules are built is through these weights and these transformation functions that we encode in a network. So I think that's a high level understanding. You won't really understand till we start coding. Now, to get into this concept, and at this point, doesn't anyone have any questions? I'll take that as a no. So now I'm on the Jupyter notebook. This is the PyTorch basics script. We are at 10:40. We're gonna start doing some coding. So how do you express this x, right? You cannot tell a computer 3 variables. You cannot say age something. It doesn't know what age is. So you first have to represent this information in a vector format. You have to say if your x1, x2, x3 were like 0, 1 only, right? So then you said you made a vector which looked like something like this. This is a vector. It's essentially a list. This is x1, x2, x3. These are your inputs. Then one data point can be 1, 0, 1. Another data point can be 0, 1, 1. And then you're saying, going back to this slide, income, employment. Now, income, employment, and this could be something like employment, graduate, lives in Calgary. So these are all yes and no questions. So then you can encode this information as 0 or 1. So if it's employed, it's a 1. If it's not employed, it's a 0. If it's graduate, is 0. Like if it's graduate, it's 1. If it's not, it's 0. If it lives in Calgary, it's a 1. So that's how you would take a true or false kind of data. But then this has salary, which is a continuous value. Maybe you can say 50,500 something, and then you can say 25,100 something. This is a very continuous value. Or you could break this problem down into sections below 20,000. Then 20,000 to 30,000. And then you could break down this problem into say 10, 20 pay scales. But depending on what algorithm, what technique you're using, what deep learning model you're building, you would do these kinds of transformations to your data to enable learning. If you are gonna have these very small floating point numbers, and then you are trying to relate that to something that is very 0, 1, and these are all these different features of your data set, the model may not learn them very well. So then you do data transformations or you do data balancing. And so when you also say this, this concept of distribution is very important. When you say, so maybe 10 people have a salary that's below 20,000. Then maybe you have 50 people which has a salary of 30,000. So this input feature has its own distribution, and it's like if it's essentially a histogram. It's essentially this many people has this many like that much salary, that many people has that much salary, and then when you have a lot of histograms, it becomes a more of a like a normal distribution or whatever that natural distribution is. And then 0 and 1, maybe being employed or not, maybe like 1,000 people, 100,000 people are employed, and only about 1,000 people are unemployed. So this distribution is very different from their salary distribution. And when you are putting these data points together to predict something from a network, you might run into some problems. And that's where conditioning your data set, going through different transformation of your data set comes in the picture. But we are going to go into more of this when we actually build some models that solve problems and we construct the idea of the problem in later parts of this series. For now, how do you tell this computer that this feature is together? This is one feature. For this, you need to represent information as these lists, as these arrays. So in PyTorch, and if anyone is familiar with NumPy, in general PyTorch is external kind of a layer on top of NumPy for most of these data manipulation functions. So if you're familiar with NumPy, PyTorch is very easy, and that's why PyTorch is becoming more and more popular, because people already know NumPy, most Python developers, and then the transition to PyTorch is much more easier than some of the other platforms. So these are some of the basic functions in NumPy. So this is how you import NumPy. You said import NumPy as NP, and then you create an empty array of dimension 2 rows and 3 columns. So each list is 1 row, and then each of the elements in that list is 1 column. And then you have created one data point that has 2 different kinds of X, and then X has these 3 different values. And then depending on the problem and how you're formulating a problem, you might want to make different kinds of arrays. And so you do the same thing from NumPy to Torch, Torch empty, and then you have other functions like random. So empty creates a list of zeros. Random will randomly initialize these vectors. Ones will put 1 in all the data points. So these are the different kinds of initialization default implementations in PyTorch. Now you can look at the data type. So you can mention or specify the data type you want. In when you're calling this, you can say a float or a double. By default, if you have not mentioned something, so let's do a data type of a default something. So in A, I did not say what D type it should be when I created this object. So by default, it's float 32. And these things are not that important right now, but they become very important when you go, build really big models with a lot of data on CPU versus GPU. How much, what is the minimum memory one data point needs to consume to have good accuracy, but to consume as less memory as possible. Those are some real practical applications. So it becomes really important when you're trying to build production level models, but for now, maybe the data type isn't that important. And then you can add to tensors very simply like this. There are operators like size that will tell you the dimensions of one array or one this tensor that you have created. So I created E with 10 2. So it had 10 rows and 2 columns. So that's what it looks like. And then it dot size gives you this back. Now you can also do many kinds of data manipulations. Just look at something in part. This tells you, so this was my B. And then when I do all the elements in the 0th row, so this returned, so all the elements in the 0th column. So this returned me this data, this for this element and this element. So you are essentially, what this is x1, x2, x3, x4. So this is x1, x3 that's been returned here. And then when you do this, that is all elements in all the columns for your row 0. So then it returns you x1 and x2, which is this one. Now you can also just take out one element. You can say just return this v11 element for me, so which is this one. So how indexing works is this is 0 0 because this is the 0th column and the 0th row, and 0 1 1 0 and 1 1. So then you can index something and just get that item. If you didn't say item, it would return you a tensor, because internally once you have declared something as a tensor, every element in it is also a tensor, but you can get the content of that tensor by using item. Now you can declare or convert a list. So if you had a list like this already, maybe you uploaded this from a file or something, you can just call it torch tensor on that list, and it will create that tensor for you. So this is just a one-dimensional tensor like that just came from the list, and by default it's a float 32, so it will add these floating point values for its default implementation. Now many times the kind of data that you have from a file or from a natural data collection process and what actually needs to go inside a model are very different. So you need to manipulate data in very different ways. So if B was like this, you can flatten this B into a continuous list and make it like that. That function for that is a view function. And Torch now also has a reshape function which is the same as view. And if someone has background in NumPy, NumPy has this reshape function, and most of these operations here are just the same as NumPy. So here what you did was you took this array of two lists that were then one bigger list, and you flattened them out into one list of 4 elements. When would you do this? Something like this you would do in a basic model of say an image processing. If you had a 4x4 image that only said like had 2 blocks, and you wanted to just say which block was a dark color and which block was a light color, and it only had 4 blocks or 4 pixels, and so it's a 4x4 image. How you would feed that simple image to a simple network is just you would flatten it out into a list of 4. So instead of being 0 1 0 1 or being blue yellow blue yellow, it will be blue yellow. So what I'm saying is instead of being blue yellow yellow blue, now this you would have made this blue yellow blue yellow. And depending on what model you're feeding it into, the different kind of data may be important. If you're sending it to just like a simple linear, like a multi-class perceptron network, this is how you would send it. But if you're making like a convolution network, this is how you would send it. But I mean, it depends on how you formulate the problem.
Why is that? Why is it different depending on the model that you're sending it to?
So when you have say a model architecture that looked at and this is just one image, right? And this had these features as each of these pixels. So now x1, x2, x3, x4, you can just send this to a network, somehow, and say this was your block, and you want to send this to this block, and you want to put this information like 1 2 3, like so. You would just arrange this one data point as one continuous list, but then you might also represent this information as this blue yellow being this whole first row, and you then inputted this is like a very basic example, but you inputted to your algorithm this both together, and this both together, and then this together. So these and so how you would get to this state is by using a filter, but it's a slightly more complex understanding. But if there was this was a convolution neural network, there'd be a filter, kind of like something like a box that goes over this data, and it says, okay, this is blue and yellow, and there's more data here, right? This is like a big image, and this is a red and a green, and there is more data there. And so you would pass a filter on top of this data, and then it will come up with a representation for this part, it will come up with a representation for this part, and for this part. And this is something like you would do something like an edge detection. If you are not trying to figure out the whole image or what this whole image is, but say you are trying to figure out, you're trying to predict the lines between objects inside that image, then you're more interested in when these transitions happen. Maybe this was yellow for a long time, and then it starts becoming blue, and blue and blue. So this change is very important. This is a very important characteristic of your image. And so you would condition or like transform your input data to something like that captures these transitions better. This is like coming up with a representation of your input data that has this feature specially extracted out. Whenever these transitions happen, that becomes a special feature for your network. And you can, do different things. You can say, I'm interested in both. I'm interested in the whole image. I'm interested in these transitions. I'm interested in things that are more intricate patterns. Like if you're trying to differentiate between two paintings by two different artists who have very different artistic styles, then everything, all the information is important, and a network needs to learn all of these abstractions. And you can write your own functions, write your own transformations to this input data in different ways, so that you can capture these edges, these edges, and then in between this, and maybe this blue isn't really blue, this is 0.1 intensity blue, and this is 10 intensity blue. So what this intensity is, what is the gradient of these intensities till you go to a green, and then what is the intensity of this green. So there are many transformations you can do to an image depending on your task. And these kinds of thought operations on data or on one array of these values will help you formulate that transformation or design a network that will help bring out these things in different ways. Now, a lot of this stuff is already pre-implemented, over years and years. And when PyTorch and these libraries were built, you may not need to build all these transformations from scratch. There are existing methods that we're going to learn how to use. But if I were to build something completely from scratch, totally my new network, then I would need to build all of these manipulations myself, to build each state, each kind of thing that I wanted from it. And so these transformations help in doing that. And internally, PyTorch does this to your data when you use their vanilla networks. So does that answer your question?
Yes, I think so. So, I mean, again, we've probably dipped into a lot of different areas where people might be unfamiliar with image processing for that, and even edge detection and stuff like that. So, but I kind of understand what you're saying in terms of using PyTorch as the way to build up the framework that you then input into testing your model out. Is that correct?
Yeah.
Okay. So we're basically setting up all the parameters, setting the and then basically how are we going to process the data? So we have a data set, A, B, C, D. How are we going to process that? That's basically what we're setting up here.
Yep.
Has anyone else used PyTorch at all? And I have not, so.
Yeah. I mean, if you're not doing this along with me, this might be a bit boring, but this is very important to actually start coding and to debug the code and understand what's going on. So I'm gonna link, here there are links for follow-up. So these more details of what these functions are, what explanations and stuff are these two separate tutorials that people who really want to do this hands-on, going forward, they should go back and do those full tutorials and go through this script, and then we can starting building more complicated things with this. So essentially, So now this was your B, and then when you did a reshape, you can give it a finite definition. Say I want 1 row and I want 4 columns, and then it gives it this reshape. It takes this whole element, and this whole element is in one box, and it takes that one whole element into this 1 row 4 columns. This is like taking that yellow blue box to like a line, and then if you give it a -1, it will figure out what the other dimension needs to be. So if I want it to figure out how many rows it needs, I give it a -1, and then I just tell it how many columns I need from this. So this is how it reshapes the data itself. And so here I gave something 10 rows and 5 columns, and I told it figure out how many rows it should be, but I need now 10 columns. So then what it did was it took this 5 elements in one row and this 5 elements in one row, and it put it together into one row. And that's how it comes up with 10 columns, and then it figures out the other dimension from the total number of data points there is. Now, this is depending on what you're trying to do. Maybe what you wanted was you just wanted to invert this image or this array. You wanted whatever was row before, now make it a column. That is a simple of doing a 90 degrees shift on a photograph in your phone, right? You're just transforming your horizontal axis to a vertical axis. And transpose is the basic operation that happens to your image on your phone when you click that rotate button. So if I do a torch.transpose on that tensor, and then I say the axes along which that I want the transpose to happen, it just transposes this thing the other way. So then instead of saying like this thing together, this thing, it transposes that information differently. So depending on what you want to do with it, these transformations become very important. Today, we are going to build a network with some default data. And this default data is already like pre-cleaned, pre-transformed, and is exactly the way it needs to be for the model to learn from it. But when we start using real-world data, we will have to use these transformations ourselves to build that initial data set. And so then these things become very important. Some other useful functions is these linspace. Linspace is like starting from 3 to 10, split in 5 elements. Then I is like a self multiplication matrix. So anytime if you have a matrix that you multiply with this sort of a matrix, so if you had a 3 by 3 matrix of any kind of data in it, and if you multiplied that with this, it will return you that same tensor back, which is very useful operation when inside networks, when you're doing multiplications and things like that. Now, these are like the different kinds of operations that you can do. Now, another important aspect is that when you do all of these manipulations, maybe you are doing it in NumPy or in basic Python, because you're going through an iterative process, you're more comfortable with NumPy, whatever may be the reason. So then PyTorch gives you a very good ability to go from NumPy to Torch using these simple commands. So now this B was a torch. Now you've just taken the NumPy out like converted the torch tensor to a NumPy array, and so before B was a tensor, and now C is an array. Same way, if you had an array to begin with, you can take it to a tensor. And so now this NumPy to tensor, this operation is mostly useful for CUDA versus like GPU versus CPU. Now, another very important aspect of deep learning is the GPU processing of it. GPUs are, like, from a very basic level understanding, is what renders your screen when you're working on computers. Now, inherently, your screen is a matrix and you have many pixels on that screen. So GPUs were designed and evolved and built so that it can process each of these pixels at the same time and very fast. So that inherently GPUs do matrix mathematics and parallel matrix mathematics very well. So when this deep learning applications and more data came in and this boom happened, this was really enabled by the use of GPUs, because you want to compute a lot of data simultaneously, do these simultaneous processes in different parts. So if you're looking at your monitor right now, and you're looking at this PyTorch, you're looking at this gray zone and you're transitioning to this white zone, and then something goes into a black writing. So these are all edges, right? And these are all pixels. The GPU is being told right now that color these pixels gray, color these pixels white, color these pixels black. And every time I click on a tab, it's refreshing, the GPU is refreshing this information internally and updating. And so nothing changed here, nothing changed here, nothing changed here. But when I am telling it to change this, it is printing out this stuff, and it's doing this real-time manipulation of this matrix, but it knows only that this part of this matrix needed some change. So what it does, it doesn't really do all the processing in this part, all the processing in this part. It does this processing at where it needs to do it very fast. And this is like how GPUs are built, and this is something we really make use of in deep learning, because we need to do these kinds of manipulations to arrays and vectors of data. Another thing is that when you're taking this NumPy data to a GPU, you need certain syntax. Torch gives you these CUDA functionalities. CUDA is this basically how you talk to your GPU. And when we go into building models and things like that, we can talk more about this. Today we are only gonna do things on the CPU, but on a Mac you won't have a GPU. These are mostly NVIDIA. CUDA is in NVIDIA, but there are other ways of doing GPU. Torch gives you a CUDA implementation. So you need a NVIDIA graphics card for this. And we can also do this on the cloud on GCP, where GCP will provide you off-the-shelf GPUs and all set up to go for these kind of processing. So you need, when you have this basic tensor, this is right now, this is on your CPU, this X, but when you do Y and you take it to device, then it makes a copy of this X from your CPU to your GPU. And also to know that this is a very expensive operation. Most of the time, a lot of the time in training, in doing different manipulations goes into this, where you load and unload data from your GPUs to do different kinds of transformations, save things and evaluate things and stuff like that. So doing this in an optimized way, in a reasonable way, is very important. And so that's why PyTorch has taken away all the problems from you. It has done the best implementation possible, and so you don't have to worry about it. It will do all that. So now we have like you can run these things yourselves for better understanding. When you are doing this, you are saying, and this is like a very complex nested structure. You're saying, I want two data points, and then I want each data point to be this one whole thing where I have these two instances of something, and then each instance is again by itself one thing, and then one thing has two elements. That's what it looks like. Now it might, in the beginning, it's very difficult for people to understand why you need to have data in this format, but that's where the GPU part and this loading unloading data comes in. When you are maybe your GPU has the capacity, and if you look at GPU ratings and stuff like that, at a time, based on how good a GPU is and how strong a GPU is, at a time it can only process so many things at the same time. So that's like a batch. Before, depending on what floating point you use, if it was a float 32 and you use a 64 batch, you would consume certain memory, and that memory needs to be less than what a GPU can handle. If you used an int, which is like lot less memory, and you use a 64 batch, then your GPU is it can handle it. So then you can increase the batch of processing. You can make this to 128 to fit in that GPU. And now each batch, this is what that, when you work with data, this is what it looks like. 2 is here a batch. So you are saying at a time, my GPU can only process 2 data points, which is not true. You can do more. But so this is like a batch. Now inside a batch, you want to maintain each data point as a separate entity. So that's why you are enclosing each data point into one separate instance. And then you are saying each of these instances have two elements that themselves are separate things. So maybe this is entirely one row. This is entirely another row. So you want to maintain this distinct aspects of the data. And it depends. Well, you may want to flatten out this part only. So when you only say like flatten the whole data, you will flatten out the whole batch. And you never want to do that. If you say I had a dog and a cat and a parrot in my data set, and in one batch you had 3 dogs, 4 cats, and for 10 parrots, and if you merged everything together into one flat array, there is no information, like a lot of information is lost, and the target of predicting something as a cat and dog won't be achieved. What you need to do is you need to flatten out this information into different lists, which keeps that this is a dog, this is a parrot, this is a cat, but all of these things together are in one batch that I'm going to upload onto the GPU and unload off the GPU. So these transformations in PyTorch are very important, and important to understand what each element is, what that size is, and when you upload your own data, you need to kind of look at them and understand it. So squeeze and unsqueeze is again a very handy function where you are doing this batching, unbatching process, and it essentially squeezing is like you remove all that batch information, put every distinct element just together like a stack, and when you unsqueeze it, you just make these into separate batches and separate entities, and depending on whether you're trying to save the data, load the data, what kind of model you are learning, you need to do all these kinds of transformations. You can also do some conditional operations, like you can say if x is greater than 0 and this is my x, and then there are some negative elements in different places, and I'm saying if x is greater than 0, then keep x or put y. So then what finally it comes up with, wherever there is a negative element, it changes that to a 1, which was this y values, and the rest it keeps in x. What also happens is a mutation of the data type, where it will take that original x data type, how many floating point values that was, and it will convert the y to that value. Now, one more very important thing in Torch is this requires gradient function. Now, this somebody talked about loss earlier. So what this loss is this difference, right? This change or this difference or this not good enough factor, which in very mathematical terms is a gradient. It comes from a gradient. If you cannot compute the change of something, so x went to x1, what was this x1 minus x, and why you call this a gradient and not just a difference? Because it's on top of x. What degree of x changed? It's not just the absolute value of x, it's this what percentage of x changed. So that is by definition a gradient, and the whole system of training a network, learning parameters is dependent on these computations of gradients. And PyTorch does a very good default implementation of these gradient updates. It's efficient, so you don't have to like write all that boilerplate code, and it's done the state-of-the-art best job that you can do with the gradient computation. So when you're declaring a tensor, in the beginning, you might know which parameters requires gradients and which parameters don't. So if it's something is your input data, and say here x was your just like 3 continuous values, and this came from your data, then you would probably not say it requires gradient, because you cannot change the data. You cannot say what's the point of updating your input image. That's you're actually corrupting the information that has been given to you. What you need to keep the input image as just information. The labels that are y, that is also just information, that is the ground truth. What needs gradients are these weights. If a model has weights from this one layer to the other layer, that learns that function that predicts this y, depending on how close the predictions were, using that loss, you will update these weights in the network. So then the weights need gradients. So if you had declared a variable that was for your weights, then you would say that this needs to be true, because you want that computation or these tensor to be updated using gradients. And if you set this to false, you can never update the gradients on it while computation. And there are many things internally to this. You can, we'll go into this, but when you're training a model, you can say torch no grad, which is like you're turning off the gradient updates, and you do something, and then you say you update the gradients. But if you don't have this set to false in your input data, by default it will update everything. So by how the data is loaded, unloaded, the values, there are a lot of default implementations, and also you can do it yourself. You need to make sure that you only have your requires gradient to true when it's a weight, or it's a tunable parameter, or it's a learnable parameter in your network. It's not your ground truth, or it's not your information. And then you can do basic mathematical operations like multiplications, power, get the mean. These are very similar to your NumPy. Now, this is the most magical thing about PyTorch. All this gradient updates is a backward function. backward function, and if anyone is from signal processing or control theory or engineering kind of a background, what control theory says is that you have a forward pass, you generate something, and then you look at how what you generated, what was good enough to the truth or what you wanted to generate, and then you feed back or you do a backward pass of your network propagating this difference. And it's the same thing in a deep learning model. It's a control system where you have taken the difference between what you wanted to generate and what you have generated, and you're doing a backward pass. And this backward pass is what updates these gradients, updates the control function, or these weights inside the network. So this backward will do everything. If I had my x gradient false, it will not have a gradient. But if I have an x grad true, then it will update it. So now it's also a concept of what was this thing that you propagated backwards. So for this you need this mean, and then you do the propagation of loss on your mean value. This is just for example. Mean can become loss, or whatever unique thing you want, based on this difference, which is a scalar value, which was your loss or whatever the difference was. Based on this loss, when you did this backward function, it updated the weights, or the whatever tensors that created this scalar value, right? So that's what this backward function will inherently do. And then there are different ways of saying this requires gradient, does not require gradient. You can turn whenever you're doing a block of operation. Usually this is the preferred method, torch no grad. So then you know exactly which part of this code you ran without any gradient updates, and then at the declaration you have specified which tensors needed gradients and could update gradients and which ones couldn't. So this is like the basic introduction, and to really get familiar and good with coding these things, it's very important to understand those concepts.
Is there anywhere that you know of that sort of explains these concepts that people can go to after the fact? So one thing that I think is challenging, not having used PyTorch, is the different variables of the functions. So, for instance, when you're looking at I don't know, just one of the variables, you said, well, this part of the variable is this does this thing, and then the second part of the variable does this thing. So do you know of anywhere that sort of explains those different functions that we could take a look at to understand? And then the second thing is somewhere that explains why we might want to use those functions, and just getting used to them.
Yeah. So one thing I did, because we have 2 hours and this is like an entire library and basic level introduction to deep learning, and this is a lot to cover. So what the first part 1, the philosophy would be, I take different YouTube tutorials and documentations, and what I'm explaining here, all of this is done in more details in these 2 tutorials. These tutorials have some bits more that we're going to cover next week as well. But in general, this is like the basic thing we're doing today. And so anybody to really get an understanding should go back to these tutorials and follow along. And these are like each 6-7 hour commitments. It's not a 2-hour thing, but if you have some more because these guys kind of skip over the introduction part or why we are doing it, so that's what I've been kind of concentrating on explaining. But all of this stuff that I'm doing is there, and then documentation is always the most important, like depending on how advanced you are, right? Like if you're familiar with programming, documentation might just be good enough. If you know Python, just go to the documents, they explain everything, they explain the mathematical formulas for everything, and why they what exactly transformation is happening to the math, to the matrix underneath. Everything is explained in this document. All of these are all the basic operations. It will tell you what it returns, what dimensions mean, what is actually doing. Another important or useful thing to do, that you can do, is also say if torch mt. This is an easy way of looking up documentation. This in a notebook, this by just doing this question mark after any function, it will give whatever is documentation is in here. It pops up. It tells you what everything is, what needs to go in. It's kind of like inside an IDE. When you do a tab, it shows you what parameters it needs and what kind of some more details, and then you go to the implementation. But in a Jupyter notebook, you cannot do that. It doesn't show you suggestions, which also makes it a good environment to learn things, because you don't, like, it doesn't autofill stuff for you. But then if you need the documentations, you can just do a question mark and then it pops up. And
Cool, good to know.
Syria, could I just jump in here? So I'm going to try to explain what I understand. In linear algebra, you have like a system of equations. You have independent and dependent variables, and to solve a system of linear equations, you have say n observations, well, n unknowns, and you have n observations. So in this case, and if you have more observations than equations that you want to solve, you've got sort of redundant observations. So now, sort of take from that, how does solving these models, do you have redundant observations, or is it just the number of the number of independent the number of variables that you want to solve and the number of observations are equal? Does that make sense to you at all? I mean, I'm just trying to fit what that in this case here, what you're trying to solve.
Right. That is a very good question, and that is exactly what we're trying to do on a high level, right? So when we're trying to solve a set of equations, we know at the beginning if this is a quadratic equation, if this is a polynomial, if this is a linear. So we know what family of equations there are. So we know how many weights there should be to solve this equation from x to y. Now there might be redundant, and when you're doing these matrix mathematics, these redundancies or things that don't have rank. That's how we would say that in linear algebra or in conventional mathematics. A sense of if the rank becomes a 0, then those are redundant on your x side, and those don't add value. But when you do machine learning, when you do deep learning, you have absolutely no way of knowing what is redundant, and if anything is at all redundant. And there, in reality, a lot of information is. And we train models in different ways to deal with it. So dropout is one big example. where different weights are dropped out randomly in different logic to deal with this. So if you had a data set which had a lot of same information just in different formats, and the model was too complex for it to like it overfit. So it said, okay, cat and dog, 100 image, 100 image, they all are black and white, they all have very similar patterns, but your network had 1,000,000 parameters. It didn't need that many parameters to understand the difference. So it will drop, then you need to then do certain things to learn this in a way that it doesn't overfit, because overfitting is a terrible problem. And then if you overfit, only those 200 images will ever be recognized by that network. So generalization of these patterns is very important. So there are different techniques of dropout, regularization, of data augmentation, transforming this data in a lot of different ways, so that you are appending a lot of stochastic noise, where you're preserving the information always. And then you have a lot of data that the model could go through, but then only the real patterns, the things that really were there in the data to begin with, that was what was learned. Because in the beginning, you didn't know how much complexity of that model was needed to not overfit to the data you had. So your best chance was to augment the data set and say, if I had this cat image, I'm gonna make this like a distorted cat, a 90 degrees rotated cat, a green cat, a orange cat, and a lot of other kinds of manipulations to it, and then give the network all of this randomness. But it will learn, if you do this correctly, it will learn which are these patterns that are really distinct between a cat and a dog, in order to make that prediction. So it's very, like, algebra is where it all started. For me, how I look at it, because I'm from an electrical engineering background, signal processing and control systems, where you really implemented algebra, and then deep learning using all these modern computing and a lot of data augmentation and inherent data collection capabilities, is applying all of this, is putting all of these pieces together to do something in an automatic way, where you're not building and drawing control systems for specific applications.
Yeah,
that makes sense.
You really have to know your data, and you don't just throw out data that you don't like, I suppose. You have to, and I know it's a tricky concept, but you really have to know and trust your data.
Yeah. Yep. And we will go in more details into all of this when we do these part 2 of this series. What kind of data is good in natural language versus computer vision, what you keep, what you throw, how much, and the distribution that I talked about, that is very important. How much of something is there? When you're augmenting data, you might generate a lot of randomness, but then if there are certain randomness which logically got generated only like 0.01% times, versus something that got generated 10% times, and how much of what is the possibility that something gets interpreted as information versus noise. These are various considerations that go into really designing, building real models that perform well, generalize well in a production environment. We will talk about more of that and how to do all of that in part 2. Right now, we're just trying to understand how to train a model and how to build it. Okay, so MNIST is a very common data set. If no one's heard of it, it's essentially handwritten digits between 0 to 1 that they processed and made it grayscale, resized, and made this good format that a model can learn from. and for us to really do something completely new, we will have to prepare a data set like that. So I'm just gonna, so this is now the PyTorch data and basic model script. Same thing, imports. Now I'm importing transforms and data sets specifically from Torch Vision. And Torch Vision is like a separate module for computer vision applications in PyTorch. And PyTorch has separate modules for natural language as well, because slightly the ideology of solving different problems are different. So the kind of functionalities each one gives is different as well. So now we are loading in the data set. So how do we, this data set is kind of like default object or default class, and then MNIST is, it's all internally set up. We can look into each of these, like if someone's more advanced, they can go to PyTorch on GitHub and look at their default implementation and how they have wired everything up inside. I'll put a link for that as well. It tells you this is a torchvision.dataset module, and then if you did .mnist, it will tell you what that default implementation is for PyTorch. It's essentially, it has a train component, a transform component. If you can say download true to false, you can target transforms as like Y. You can transform your Y differently and your X differently, and then there's explanation for each of these things. So if you don't have this downloaded already, PyTorch will download this if you set this to true. And train you can set to true, and for test set, train is false. Now the concept of train and test data is that you need to validate, right? When you were learning this process, you had this X input, you had a Y, known Y, and you were predicting some form of Y. Your every iteration or every epoch, you were calculating the difference between your assumptions or your predictions and the real Y. That was your loss. Then you computed a gradient, you updated your weights so that these weights can then lead to a better prediction. And then again, you did this a bunch of times till some condition was met, till you had 100 epochs, or till your loss was below certain threshold, or you had spent 2 days training something. There is always a condition at which point you give up, you stop, or maybe you have reached 100% accuracy, depends on your model. So when you stop training, you need to evaluate what you have learned on a test set. Now this test set is ideally not, like it should not have any overlap with your training data. So it should not have any exact same X values in your, as that was there in your train data, because then it has already learned that train distribution. It knew that model knows from the training data itself that, okay, X, when it was so much, when with Y being so much, and with Z being so much, this always leads to Y. And but if you do a 10-20% up and down on your Y versus a 30-40% up and down on your X, it leads to a different Y. So these patterns your training data has learned, and if your test data has the same data as your training, then it will be very good at it. It'll be very confident. It will, I already know this. But that's not the reality of things. Maybe you've only sampled data from of bread from one bakery, and it has learned this one chef how he makes a bread. But what about like the other bakery, the other chef in that one bakery? So every person has their own way of doing things, or every data collection, data generation, everything adds its own bias. If I collected cat images from my like cell phone versus a digital camera, that also has added bias to how good that image is. So if your training data only looked at images from like a good high resolution camera, and then you gave your test images as something you collected from your phone, even like something that had 99% law accuracy on your training set, will fail miserably on your test set, because this thing that you don't even know, you as a human, you don't even know to differentiate really between something very high resolution and something not that great. But for a model, it will learn it. It will learn how sharp these transitions were, or how blurry these transitions were, and it will generalize that pattern, and it will learn it by the time it finishes training. But the moment the test set doesn't have that sharpness, or those kinds of transitions, it will fail, even though it has other things to go off of, because it's very simple. It's a cat and a dog. So the distribution of the training and the test data is very important. It should ideally have seen enough of both images from a digital camera and a normal cell phone, to a bad cell phone, to just your laptop camera, to maybe a drone image, to maybe something that is just moving about, in a motion capture kind of a thing. So it needs to see all of these kinds of things in your train, and then your test data can also be of the same distribution, or same distribution as in like a similar but different data points of capturing the data in different ways. Or you could also have an application where as a prior that my test data will always come from phone. So mine gonna have a separate test set which only looks at phone images, and see how training this on everything improves something on my particular test set. Then you can have based on your application, you can do many tweaks. Maybe if you know already that your test set or your real application data will always come from a phone, maybe adding a lot of data from motion capture or from low resolution bad cameras or things like that is actually harming the model. It's confusing the model more, and the test set is performing worse. And so then you keep high resolution photos and photos from your camera in your training set, and retrain again till you get this good test set accuracy, which is the real distribution or the expected distribution that you're going to see when you use this model. But if your test set is actually going to be any kind of image people upload on Google, then you can have a test set that's more and more complex, add more noise to it, do other transformations to it that you didn't do on your training set, and then test that how much did it generalize actually to things that to random things that I just collected, but wasn't there when I trained it. So this train test design is very important, and is crucial for building real models. I created this train and a test, and we are in the 15-minute zone. I'm just gonna run this quickly. And so this type train is an MNIST data set, and then before you can train a model with it from this MNIST data set, so this is kind of an MNIST object, you need to make it a data object. So torch utils.data.data loader converts this implementation to a data object that is usable for training a model, which becomes this data loader. And when I'm doing this conversion, I'm mentioning a batch. This batch is 32. So when I did previously in that other notebook, that squeezing, unsqueezing, or reshaping, that's what happening internally right now. When you give it a batch size 32, it puts all of these data points together in sections of 32, and inside 32, then every data point is preserved in its own array. So it's unsqueezed everything to make sure that only 32 data points go together in one batch, but inside each 32 data points, each data entity is unique. So then you can also verify what batch size is, and then you can get the data size details. In this data set you have 60,000 data points, and so train is not a list, it's not an array, it's nothing right now. I mean, it's not a iterable object, so you cannot do this. You can convert train to a list, and make it serializable, and then do just take the 0th element to look at it. Here you can see that the 0th element now is a 32 sized array. So if I did of size of this, and you're serializing a lot of data, so it takes a while. So X is now 2. So X is a list, so X has both the input data and the label. So it has 32 images, which are like this, and each image then has its own pixel values and its own inner nesting, and then you have labels for each 32 image. There is a label. It is a 1 or a 7 or a 0 or a 5. And you want each batch to be as well distributed as possible. You don't want a batch to be all zeros or all ones or something like that. Way, when you're computing the loss will like move around a lot depending on it will not learn well. So that is why the shuffle is very important. It shuffles this data very well, so that it gets this random pattern every batch, and then it can really learn from it. And it also depends on how you collected and stored your data to begin with. So these are different ways of looking at the data. So I'm gonna take here, I did this image to be the first image and just the X. And you can use Matplotlib to visualize this as an image. So we can see. Okay, come on up. So you can see this is an 8, and so you should run all of these yourselves. You can squeeze and squeeze data and get this to different dimensions. So when I plotted this, I needed this to be a matrix of 28 by 28. But when I got the image, this image was not of that size. That image was of 12828. So I needed to remove that nesting. So that's when I did this view operation, or this is same as reshape, and I reshaped this to this format so that I can plot and visualize it. So that's when these operations need to be used, when you need to visualize it or transform it in a very specific way. So if I wanted to superimpose 2 on this image, and I needed to like verify and see how this augmentation is looking, I would probably first convert it into this format, do some multiplication operation between those 2 images, or some other kind of convolution operation on these 2 images, and then come up with a representation, and then I can load it back up again using these unsqueeze functions, so that it gets to that batch format that can be trained. And this -1 is always a good way of doing that if you're not sure of how much or what other dimension that it needs to be. Now, another important thing is that if you're trying to predict between 0 to and 10, or there are 10 classes that you want to predict, for this training to happen smoothly and for good accuracy, you need a good count distribution of your data. You want ideally for each image or this each label to have equal number of data points or representations in your data set. This is called data balancing, and in real world applications this rarely happens. Like when they created MLS data, they did a lot of things to make this true, but we are just using this for now. We can see that everything is between like a 9 to 11%. So if you split your data, you would have like almost around 10% share of these 10 classes, which is ideal. So this is okay, but if like you had another image which was like 19 and that was like only 2% of the data, then likelihood of that 19 being classified as a 9 is very high, or 9 or a 1, or some garbage depending. So the distribution of this input data labels, of the noise in your input data X, and the distribution of your Y label, these are very, very important. So this is like a verification. When I did this, what I did was I counted how much label, each unique label, torch.unique will give you, so this is 10, and then for each unique label, what is the number, and then what is the total count, you're adding it up. And this comes to your total should come up as the length of your all labels, and that is the length of your each training data and how many batches there are. So now we are gonna train a model using this data set. We are using torch.nn.functional and torch.optim as so there are 2 concepts here. So if I, in that network diagram, if I just said X, go to this state Fx, F1x, and then this was just a W1, and so X times W1 gave me an Y prime, and then W2 Y prime gave me a Y double prime, and that finally gave me a Y. Then this is the same as saying just a big W Y1 to Y, because if this is, it's a scalar, Y W is a scalar value, and that is going from x1 whether you are multiplying 2 different scalar values or you're multiplying 1 scalar value, it's the same thing. So when you are training this network, it's not just the weights that leads to the other state, it's the non-linearity that you can add in this model that's actually gonna make this a function. And non-linearity is a either a very simple or a very complex concept depending on your background, but it's essentially saying that my state of this Y prime is not just governed by X and W. It is a operational state of this composition that this W and X gave me. And this operational state can be different based on the kind of model that you are training. ReLU is a rectified linear unit. It's like till it is zero, it is kind of like a zero. So if your X if your X was 0 0 0 0 and then it became 1 1 1, then your Y would in a linear unit like that would be 0 0 0 0, and then it becomes some W W W W W. In a rectified unit, it's like something like so very small beta 1 beta 1 beta 1 and then W W W. So it's essentially a trigger kind of a thing that once I have this information of X and W in this neuron, and it's come there, then I'm going to trigger this neuron in a certain way. And it's also how our brains are believed to work, that you have chemical signals that goes through certain transformations and it comes to this neuron, and only when this signal is of a certain threshold or of a certain value, then it triggers that neuron. And these neurons are triggered in different rates depending on what the neuron is for. Like if your reflex action would be a very fast neuron trigger, but if it's a learning process, you're learning to dance or you're exercising or something, then it's a slower learning process. And I emphasize on the learning part because then learning rate is very important in this whole process of how much trigger, what kind of trigger, and what is the learning rate of this whole triggering and backward pass and strengthening this information process is. So this is very interrelated. So unless you have these trigger operations, you don't actually learn a neural network. These operations are what makes a neural network something that tries to be like a brain. Otherwise, it was just a linear algebra or algebraic function where just W components added to X, and then different X's came together to form different quadratic or polynomial functions or something like that. But these ReLUs are what makes this learning process possible. So this is a very simple network. We have 3 fully connected layers, and each layer has 64 neurons. So going back to this image, there are 3 levels like this, and each level has 64 neurons or 64 units. So that means from your input data, you can have correspondingly each input has 64 arrows here, then each unit here or this neuron here has another 64 arrows there, and there are 3 layers like this till it finally goes to 10 classes, which is like finally there'll be 10 points here. So your 64 hidden points can go to these 10 points, each going 64 arrows. So in the implementation of how this network is going to train and how it's going to load this data, it's going to switch off these gradients on the data, keep the gradients on the weights. All of this is a default implementation inside NN module. In this PyTorch has done a lot of these things that we talked about, where input data shouldn't have gradients, weights should have gradients, then weight connections between one layer to the other, and all of that. What we need to do is import from the base class, initialize the functionality of the base class, and then say what is the model architecture. The model architecture here is 3 fully connected layers, each layer with number of neurons as 64, and then input dimensions. So your first layer has 64 neurons, but it's getting data from these input images. Now, input images here is 28 by 28 pixels, right? So this is your input image, but in this model, we are flattening it out into one array of whatever this product is. So 28, 784. This is one array. Each input X is now your one array of 784 elements. And so then your input dimension to your first fully connected layer is 784. And then it's the number of neurons. So this is your connecting you're connecting these. So here you had age, income, employment, 3 variables. Here you have now 784 points where x1, x2, x3, each value of each pixel is one input. And so then this fully connected layer is showing you this part of the network, this connections where 784 is going to 64 units. And then the next one though goes from 64 to 64. So it's number of neurons, 64 to 64. And then the final one goes from 64 to how many classes you have, which is 10. So then each block is built, and how this forward function you implement will determine how the input data, that X array, is processed in through these different layers. So like I said, ReLU or an activation on each of those units is important. So you're going to do a ReLU operation on each of those units inside each of these hidden layers, and then the final layer will have a log softmax. Now, what is these activation functions for different problems? It's different. If it was a binary classification, you would use like a different kind of a function. If it was a linear, like a regression problem, you would use a linear. So we will talk more about these things as we go deeper into it. But right now we are gonna say log softmax. So what this does is it takes probability that this input X is of these 10 classes. So it comes up with these 10 different values, and each value is a log probability now after this transformation, that it's a value of this being a 1 or a 2 or a 3. It becomes a kind of a floating point value. Then you take, it's not a 0 or a 1. It is not an array that comes out that tells you 0, 0, 0, 1, 1, 1. It is a softmax value. And then you take the argmax of that to then do the back propagation, where after doing that argmax thing, so from this soft value of 0.1, 0.3, 0.7, 0.25, 2.8, which was the dominant or something like that, you took the dominant one and said, okay, this is the one that's 0 or 1. It did this conversion at this final layer, and then you can take the loss from your actual labels and say, okay, it wasn't a 0, it wasn't a 1. So all of these are correct. So there is no loss there. So 0, 0, if it's a 0, if 1 is a 1, there is no, the loss component is 0. But if it gets a prediction wrong, where it's a 1, it predicted 1 for something, and it predicted when it was, so there's a mismatch there. It's 1 for something where it should have been a 0, and it's a 0 for something that should have been a 1. So then there's a loss getting captured there when it got something wrong. So that is what is going to get back propagated. Now this is like the basic network, and it just has these forward operations. And now PyTorch, you can either create this object and then pass a data point through this, or You can also just call it with the object declaration itself, like not there's no need to call the forward function explicitly. This is a default implementation of PyTorch. So here I've created this object of this neural network. I either can call dot forward on it, or I can just do the object and pass the data to it. It's the same thing. And then how it's going to learn this. Now here comes the optimizer, and the epoch passes to the data, each data batch in the data, computing the loss and doing the backward. Your optimizer function is essentially when you get something wrong, when you have this loss, and you have this loss over a batch of things. It's not just one data point, you have a batch loss. Now, how this loss is going to get optimized to compute these gradients will be another function that's determined by this optimizer. And this optimizer has a learning rate. How fast I'm going to learn these parameters, and how I'm going to update these parameters. So sometimes if you just have like one step function kind of a thing, and then one big learning rate is just goes from this one batch value to another batch value, and it's like moving around, and it takes a long time to learn, or it doesn't learn well, it just saturates at some point. And this is a more complex topic, we can talk more about it, but essentially optimizer is how it's going to upgrade these gradients over these batches, and condition the learning process. Now you have epochs. Epochs is how many parses of the full data set, and then when you're parsing through a data set, you are parsing through each batch at a time. So you're doing X and Y, you're splitting, because we saw before that each batch had data 0, 0 and a 0, 1. So 0, 0 is your X and 0, 1 is your Y. You first make 0 gradients. You don't want your gradients to be updated. Then you pass your data to it, and then you compute the loss. And then when you're doing when you have computed this batch loss, you're doing a loss backward, and you're updating the weights for that batch, and you're doing an optimizer step. And it's saying how much of this loss function I took into account, of how this learning rate I tweaked based on this loss. And it's a complex process, and it did this for each batch in each for this whole epoch, and then it computed a final loss after this one batch or one epoch was done. So now what this is doing is, this is the actual training process. Before, I just created a network that could do some operations on a data to given label. But when you are actually doing the backward, evaluating your hypothesis to the actual output, that is when you are doing an update or the training of the weights. So this is gonna run for 20 epochs. Or maybe I can just do it for 5 now. At the end of this training process, then you compute the accuracy on your train and your test. And when you're computing the accuracy, you do not want your gradients to be updated, because that's cheating. Because if you're learning from your test data while evaluation, then that's again a training or an update process. You don't want that. So when you're evaluating something, you do not want anything to get updated. You're fixing your model, you're fixing all the weights, everything, and then you are evaluating on the performance. So I've finished training. And this is what you're doing. You're taking an argmax and you're evaluating if this is correct to the actual label, and this is a correct in the total. So then you get the accuracy over the correct on the total. And we saw with this data, even 5 epochs gave you 96. And sometimes increasing epochs doesn't help. Like even if I did 100 epochs, maybe it won't go more than 97. There are limits to how much a model can get out of a given data set. And that also is a good thing, because then that controls overfitting and generalization, and we can talk about that later. So it got a 95% accuracy on the test set. And considering this data set, train and test are very much in the same distribution, this is not surprising, right? Like it's the same process of collecting data, processing data. It's the same way of, different ways of writing digits, but from the same pool of things. It's not like I am now writing numbers on my iPad and putting that data in my test. If I did that, then we would actually know how much the model has actually generalized. And then we can do a bunch of runs and see how good it gets. So it predicted a 2, and it's actually a 2. Now it's predicting a 4. It's actually 4. So it's pretty good. So this is essentially the steps that we did. These are the different operations. Okay.
It's awesome.
Right. So to really get something out of this, you should run these scripts yourselves. And I highly recommend going through those video tutorials. There are 2 of them. They go into more details, but I mean, depending on where you are at, you may not want to do the full thing. But do at least these parts and really get familiar with writing this stuff, and then we can build from there. As we progress, I'm gonna do some more PyTorch maybe next week, because Kira's is also very similar. It's also a very object-oriented construct, but TensorFlow is slightly different. You have to understand some graph computation for that. But once you have done these basics on the 3 different tools, we are going to actually start looking at real data sets and what these optimizing functions are, what losses, which loss to use when, based on what problems. And there are tons of books and materials that I'll link you to. That's the plan.
Perfect.
Okay.
Well, that's great. Thank you so much, Suryatapa. Is there any questions at this point? And we can jump into the materials after the fact.
Greg, will this presentation be posted somewhere?
Yeah, the presentation is available, Mahesh. If you go down to the bottom left-hand corner of the Meet screen right now and click the little up arrow, it gives you details about this meeting. So it says AI Fundamentals. To the left of that is the attachments, and so the presentation is there. If you're wondering about the video after the fact, we are recording it, so we'll hit record. Once it pops into Google Drive, I can share a link to that to Meetup, so you can take a look at it after the fact.
Fabulous. Thanks, Greg.
Yeah, for sure. Okay, perfect.
Great.
Just want to say thank you. Go ahead.
Yeah, so I hope all of you will show up next week and we can build on this. I'm really looking forward to actually getting something out of this series where, as a community, we can build something and have real outcomes. So it'd be great that if people stick to it. Thanks.
Yeah, absolutely. Thanks, everybody, for joining. Really appreciate you taking your time on a Sunday morning. Hope you're all having a great long weekend. Thanks, Suryatapa.
Thank you.
Yes, thank you very much. Some deep learning on a long weekend. Perfect for us. Yeah.
Okay.
Thank you, Shreya and Greg.
Thanks a lot. We'll talk soon.